Lattice-based cryptography schemes have emerged as the frontrunner in the race to post-quantum cryptography. My goal with this video will be to simplify and explain what lattices actually are and how we can use them to create this hard and easy puzzle framework that's found in other public and private key encryption schemes. This video will be mostly visual, focusing on building up an intuition of what's going on underneath the hood rather than relying on mathematical proofs. You might already have a mental picture of what a lattice is. You probably envision some kind of three-dimensional set of points, but mathematically it really starts like this. Let's say we have these two vectors, both shooting out of an origin. If we start to take linear combinations of those vectors, so say minus blue minus red, minus blue plus red, and etc., we start to fill in points at the end of each of those linear combinations, we start to fill in a lattice. It's important to note that this is in 2 dimensions for the sake of my CPU, which is rendering all of these animations, but lattices can be in essentially infinite dimensions. Now, to illustrate an important feature of lattices, if we look at these two vectors, which look very different from the ones we just saw, and we start to fill in their points, we intuitively get a very different looking lattice. Or so it seems. What ends up happening is if we finish filling in this lattice entirely, we get the exact same square grid as the ones we got from the vectors we just saw. This is a really important point, as it emphasizes that two pairs of vectors that can be completely different can generate the exact same lattice. Now let's look at a whole other set of vectors. These two are closer together, or more collinear, and to introduce why lattices are such a good tool for cryptography, we can ask a really simple question. What linear combination of these vectors is closest to the origin? As evident by some of the guesses coming up on the screen, this is not an easy question to answer. The combination could really be anything. But if we go back to our original simple pair of vectors, that question becomes really obvious. Great, now we have all the tools that we need to understand how we can actually send a message. Let's start off with our original pair of vectors and make this good basis Alice's private key, because we know that she can use these vectors to easily solve the closest point problem that I just introduced. Now Bob wants to send Alice a message, so she sends this bad basis, which has the same lattice as the good basis. Bob picks a point on the lattice to somehow represent his message, and then sends a point that's close but not quite on the lattice. So for anyone eavesdropping, finding the point that Bob was actually referring to is really, really hard and can take many combinations of both vectors. But Alice can use her private key, or the good basis, to decipher that the point Bob sent was minus 3 red plus 2 blue. And that's it. That's the intuition behind the most simple form of lattice-based encryption, or the GGH protocol. Remember that that was just 2 dimensions, and technically we could keep adding dimensional complexity to make this scheme more and more secure. But as it turns out, this vanilla version of lattice-based encryption is not actually secure, and there's some cool tricks that mathematicians can use to reduce the complexity of the problem. However, the frontrunners of the NIST competition for post-quantum cryptography, Kyber, still use a variant of this problem called learning with errors, where they essentially inject noise into the solutions of linear equations, but because it can be directly mapped to this lattice problem, it's still referred to as a lattice-based encryption scheme. But I'll leave the details to understanding that for Param to figure out in my Python file. Also, when I woke up this morning on Thursday, April 25th, there was a preprint of a paper claiming to have broken the aforementioned learning with errors scheme, but that happens almost all the time. So we'll have to wait and see whether it's mathematically sound and keep trying to figure out new, more innovative encryption schemes. Thank you.